Hi, in this talk, I'm going to present a paper extracting variant features for prediction of state of health of batteries in hybrid energy buses. This is a work that is carried in Kaiser Research Center at Halmstad University in Sweden. I'm Mohammed Reith Al-Farabishi, the presenter. The agenda would go as expected. I will introduce the problem and talk about some related work. And then I will go to explain our method along with some experimental results and conclude with some closing remarks and some directions for future work of this research. The topic that I'm going to discuss is batteries in hybrid buses. And batteries in hybrid buses is a safety critical component. And it's essentially the most expensive component for buses. So it's crucial for its operation, which gives a lot of importance to the monitoring of battery deterioration. The difficulty here comes when considering the fact that we have buses coming from different variants and different physical configuration and operating conditions. You can see here that we have buses, single-decker buses, double-decker buses, articulated buses, to name some of the variety in physical configuration, while buses could operate also in different scenarios. Doing machine learning here in order to model the duration of the battery is challenging because of the sparsity of the data, because this is a newly emerging field, so we don't have data. This variety in configuration make it even harder because you will have even less and less data for the less popular configuration and operating conditions. And even the human knowledge and human expertise is sparse, and because this is a newly emerging field, so you even don't have that much of subject matter expertise to fine-tune whatever modeling you are building on top of this data. Usually, state of health is one of the popular measures to reflect the health of the battery in reference to its ideal condition. And it can be used as a proxy to reflect the health of battery in comparison to its ideal state, and as a measure of or a proxy of end of life. We have observed in the related work trying to predict and to model state of health that the majority of studies are assuming that the training data set or the training distribution are matching the testing distribution. And this is not the case in practical terms. In a lot of cases, it's a dynamically evolving environment, and the distribution shift all the time with new configuration and new deployment conditions. We have only seen two work in the literature which try to predict state of health in a transfer learning setting. Tan presented an approach based on LSTM, which considered transfer learning for SOH predictions. And she presented a work using recurrent neural network trained with a relevant battery, but different battery, and only fine-tuned with the early degradation cycle from the target battery. However, in this work, we are tackling the most challenging scenario in which we have no labeled data in the target. And to the best of our knowledge, we haven't seen any work which try to identify this invariant features from source domain. And by invariant features, we mean features which can work equally well between the target domain and source domain, features that can generalize well across a variety of conditions and physical configurations. In order to identify these features, we will first formulate the problem of feature selection, of invariant feature selection. We have a number of source domains with labeled data and the target domain in which we don't have data. The data is not labeled in the target. And our task is to identify a subset of features X, of which the conditional distribution between source and target doesn't change. So we will identify these predictors in which the relation between the target variables and the predictors stay the same between the source and target domain. To do so, we are going to use an evolutionary approach, a genetic algorithm, And the objective function of this genetic algorithm will try to do two things. It will try to select the smallest number of features and features which transfer well across a variety of source domains. To do so, we will measure the performance in leave one domain out cross validation scenario, in which we will validate on each fold using one domain as a validation split, and we train with the other source domain as training. And then we calculate the performance over all folds, and we consider this as the fitness of this candidate feature subset. In our experiment, we have a data set, real-world data set of over 1,500 hybrid buses, and we have tested 3 physical configuration, double-decker, single-decker, articulated, and three scenarios of operating condition based on average speed. We have slow buses operating in city centers and moderate operating on the outer circle of the city, and fast between cities, so you can afford to drive faster. In each of these scenarios, we will be training with 2 source domains and testing on the target domain, and we will not have the labels of this target domain, and we have 6 scenarios overall. The input feature represent the time and distance traveled on different modes. So we have diesel, electric, hybrid, and we have also the charge time. In addition, we have the age of the battery that is mounted on the bus. In the first experiment, we can see that our approach can outperform significantly a number of wrapper and filter feature selection approaches. And it's even better than using all features. So if you train the model with all features, we are doing significantly better in 2 out of these 3 cases. We have observed similar results with the other 3 physical configuration scenarios, in which in 2 out of 3, we are also outperforming other feature selection methods and using all features. So 4 out of 6 scenarios we have tested, we were significantly better than all other alternatives. When we rank the feature that is selected the most across these scenarios, we have noticed that total time and hybrid time were the highest ranked features. As a concluding remarks, we can see that the selection of invariant features can improve the generalization of the machine learning model, because when we compare it to a situation of which you are dealing with all the input features, we were doing significantly better in 4 out of 6 scenarios. We have noticed that the algorithm works better when you have a variety in the source domains. So as you can see here, when we train with a small chassis bus along with a big chassis, this transfer good to a target domain like the articulated. In a similar style, when you train with articulated and single decker, you achieve good result on double decker. However, when you train with double and articulated, these 2 are large chassis bus. The features learned didn't transfer that well to single decker. So the intuition here is like you need some variety in the source domains in order to achieve the best results with this approach. Total time and hybrid time are the 2 highest ranked features that we have identified in this work. And we are planning in the future to validate this approach, this evolutionary approach, with more data set to see how general this approach can be. These are the references that I've mentioned during this presentation, and I want to thank you so much for your attention.